Okay, let's dive right into this. We're going to tackle a classic chemistry problem today. And yeah, it might look a little intimidating at first glance, but I promise you, once you see the logic behind it, it's actually super satisfying to solve. We're going to crack the code of optical isomers together. All right, here's our mission for today. Take a good look at this molecule. We're going to figure out one simple thing, just how many optical isomers can it have? Now, to get to that answer, we've got to start by hunting for something really specific, kind of hidden inside its structure. So, let's get into it.
Okay, first things first. We need to break down this molecule's structure. We're on the hunt for a very special kind of carbon atom. I mean, this is the absolute key to figuring out the number of isomers. And these special carbons, they're called chiral carbons.
So what in the world is a chiral carbon? Well, it's actually pretty straightforward. All it is a carbon atom that's attached to 4, and this is the key part, completely different groups. Not 2, not 3, but 4 totally unique attachments. It's this uniqueness that gives the molecule all its potential for creating isomers.
So, how do we find one? It's a simple 3-step check, really. First, you just pick a carbon atom. Then, you look at the 4 things attached to it. And last, you just have to ask yourself, are all 4 of those groups different from each other? Let's give it a shot with our molecule. Okay, let's check out the second carbon in the chain. You can see it's bonded to 4 different things. We've got a hydrogen atom, a hydroxyl group, a methyl group, and then, well, the entire rest of the molecule's chain. Are those 4 things different? You bet they are. So boom, we found our first chiral carbon. So what happens if we do that same exact check on the next carbon, the third one? And then the fourth one? Well, it turns out we get the same result. Each of them is also attached to 4 totally unique groups. So that means this molecule has not 1, not 2, but 3 chiral carbons in total.
And there it is. That's our magic number. The total number of chiral carbons, which we're going to call N from now on, is 3. Seriously, this number is the most important piece of the puzzle we're going to find. So lock it in. N equals 3.
Okay, we've got our key number, N equals 3. Now, you might think we can just jump to a formula, but hold on. We have to look at the molecule's overall shape first. See how it has a CH3 group on one end and the exact same group on the other? That means the molecule is symmetrical. And that symmetry is a huge deal because it tells us which specific formula we need to use. And here is that special tool. For a symmetrical molecule like ours, the number of optical isomers is 2 to the power of n-1. See? It's a nice, clean, simple little formula.
And of course, that N in the formula, what is it? Yep, it's that magic number we just found. All that detective work we did finding the chiral carbons, it all leads right here to this moment.
All right, this is it. The home stretch, we've got our number, we've got our formula. Now all that's left is to put them together and get our answer. Let's do this. So let's just plug everything in. We start with the formula, 2 to the power of n-1. And we know what n is, right? It's 3. So we just swap out the n for a 3. First things first, let's handle that little bit of math up in the exponent. 3 minus 1, that's easy. It's 2. So our problem just got simpler. Now it's just 2 squared. We are so close. And what's 2 squared? It's 4, of course. And there you have it. That's our final answer. This molecule has exactly 4 possible optical isomers. Puzzle solved. So let's do a quick recap of how we got here. It was a pretty logical path, right? We started by finding those 3 chiral carbons. That was key. Then, we noticed the molecule was symmetrical. And because of that symmetry, we knew to use the formula 2 to the power of n-1. Plugged in our number, and bam, it led us straight to the answer, 4 optical isomers.
Now, solving this one brings up a really interesting thought, doesn't it? We used this specific formula because our molecule was symmetrical. But what if it wasn't? What about all the asymmetrical molecules out there? You have to wonder, what kind of formula would they need? That sounds like a great question for another day.